Welcome back to Math 104. We are studying the expected payoff of a game in which you roll an unfair six-sided die with the following probabilities, so that whatever number appears when you roll, you receive 10 times that number of dollars. We are focusing just on the payoffs themselves and assume for now that it doesn't cost anything each time you play. Our two tasks are to compute the expected payoff of the game in two different ways, using our two different methods, and to figure out what should it cost you each time you play in order for the game to be a fair game, in the technical sense of fair. That means that the expected net gain should be zero. To use the first method for computing expected payoff, that is, to find the expected payoff as the mean of an ideal data set of payoffs, we first need to find an ideal data set, and this one will do just fine. With 100 total rolls of the die. Where did this come from? This came from just taking the probabilities, which were given as two-place decimals, and just multiplying through by 100. That works perfectly fine, but we can notice that each of these numbers of die rolls is divisible by 5. So we can find an ideal data set with only 20 rolls in it, rather than 100, and it cannot be reduced any further. Let's use the smaller ideal data set to do the computation. So we have to compute the mean of this ideal data set. That means that we're really adding up 20 different numbers and then dividing by 20, but I've organized them in our usual way here. $10 but 7 copies of it, plus $20 but 5 copies of it, etc., all divided by 20. When we compute this out, this turns out to equal $27. Note that if the die were fair, each of these payoffs would be equally likely, and then the average would be right in the middle, $35. Instead, the probabilities are weighted towards the lower end, towards the lower values, so the expected payoff, the long-term average payoff per game, is only $27, significantly lower than $35. By the second method for computing expected value, we relentlessly multiply payoff times probability of obtaining that payoff. So $10 times 0.35 plus $20 times 0.2 plus $30 times 0.5. Right? We're taking each payoff and weighting it by its likelihood of occurrence. Plus $40 times 0.15 plus $50 times 0.1 plus $60 times 0.05. Please do not omit the 0 in 0.05. When we compute, lo and behold, it turns out that this also equals $27. If you obtained different numerical answers by the two methods, you would know that you had made a mistake somewhere. The two methods have to produce the same answer. So another reason why it's good to have two different methods is that they give you a way of checking that your answer is correct. Note that we could have been asked to find not the expected payoff, but rather the expected number that appears on the die. That is, of the numbers 1, 2, 3, 4, 5, 6, we could ask, what's the expected number? What's the long-term average number that appears when you roll this unfair die many times? The answer would have been 2.7, just as the answer here was 27. The computation would have been essentially the same, but with 1 instead of 10, 2 instead of 20, 3 instead of 30, etc. What should it cost you each time you play in order for the game to be a fair game in the technical mathematical sense? Knowing that, on average, you will receive $27 per play of the game means that it should cost exactly $27 each time you play in order to bring the expected profit, the expected net gain, down from $27 to exactly $0. That is what fair game means in the mathematical sense, that the expected net gain is exactly 0. Notice that you can have a fair game with an unfair die. In other words, you can make up for the fact that the outcomes on the die are not equally likely by adjusting the cost of the game to make it fair. If it costs anything less than $27, the game will be profitable for you to play in the long run. But if it costs anything more than $27 per play of the game, you will lose money playing this game in the long run. So why is this important? We've just figured out that $27 is the only amount the casino can charge you that will make the game a fair game, in the technical sense of that term, so that everyone's breaking even in the long run. If it charges anything other than $27, then someone is making money and someone else is losing money in the long run. So what's the bottom line here? The bottom line is expected value computations enable us to detect whether a financial decision like this one, whether to play this game or not, is a good decision or a bad decision in the long run.